Hello friends, welcome back to another video. This time I'd like to do something a bit basic. Let's figure out what the inverse of a 2x2 matrix is and what the eigenvalues of a 2x2 matrix would be. So a 2x2 matrix we will write as A with components A, B, C, D, and as you might know, the inverse of A, denoted by -1, in the subscript, or the power, would be defined by a matrix that satisfies the following equation, where this is just the identity. So we're looking for A inverse. I could define the components of A inverse to be x, y, w, z. And now what we need is A, B, C, D, x, y, w, z, and we're solving for x, y, w, z. We need this to be 1, 0, 0, 1. Well, this is just going to be a system of equations. So we're going to get ax plus bw equals 1. Then ay plus bz equals 0. Then cx plus dy equals 0. Cx, no, not y. Cx plus dw equals 0. And cy plus dz equals 1. Well, from these, from the second two, we can solve for z and w, let's say. So z is minus a over b, y. And w is minus c over d, x. So now we plug those in. We get ax plus minus bc over d w x equals 1, and cy minus ad over b y equals 1. So this should be valid for all x, y, z. For all a, b, c, d. Yeah, it should be valid for all a, b, c, d. We're trying to solve for y and x now. So I'll write just a system of two equations now. So x is, first I'll multiply everything by d. So I'll have d over ad minus bc. And y will be minus b. I multiply everything by b. And then I have a d minus bc. So I multiplied by minus b here and multiplied by d here. Okay, so we can recognize that the determinant of a is precisely equal to ad minus bc. So we've retained the determinant on in the denominator. Now we can express z and w. So w is just minus c over dx. So the d cancels. We get minus c over ad minus bc, and z is minus a over by, so a over ad minus bc. So it seems like we have a common factor, this 1 over the determinant of a, and then we just plug in these bad boys. So a inverse is gonna be 1 over the determinant of a, which is as expected. This always happens. In particular, a must be invertible, right? So with determinant of A not equal to 0, then we can define A inverse. And then we just plug these in. So in particular, we see that we have this switch instead of AD. Remember, let me just write it again. A is A, B, C, D. So we have this switch between D and A. And then B and C remain in the same position, but they get a minus onto them. And that's it. That's our inverse of a 2 by 2 matrix. Now, what about the eigenvalues? So, the eigenvalues are determined by the characteristic equation determinant of lambda 1 minus A equals 0. Perhaps I'll call this f of lambda. And so f of lambda is equal to, of course, lambda minus A minus B minus C lambda minus D, and the determinant of this. And that's going to be lambda squared minus A plus D lambda plus AD minus BC. Is that good? Yeah, that seems good. And now that's equal to, just by recognizing the various matrix functions, this is the trace of A lambda, and then plus the determinant. Yeah, okay, looks good. And now we impose f of lambda equals 0. Perhaps I'll write it a bit more mathematically. So the spectrum of A is the set lambda such that f of lambda equals 0. And, well, f of lambda equals 0 is going to give us what? This is just a, a quadratic. So we get 2 zeros. It's going to be centered around trace A. And then we get the square root of trace A squared. And then minus 4 times the determinant of A over 2. Or we could simplify it and put the 1 over 2 inside. Yeah, that's it. Nothing more to it. So those are the eigenvalues. We could, I don't know, we could apply this to an example. I'm thinking of doing Fibonacci sequence video. So let's take the matrix. So let's do an example. The matrix is x equals 0, 1, 1, 1. So we'll get that x inverse is 1 over the determinant of x. First, okay, let's get the trace x is equal to 1, and determinant of x is minus 1. So okay, then x inverse is minus 1 times, and then what? We switch these two, and then we add a minus here. So that looks like it's minus 1, 0, oh sorry, 1, 1, 0, and by the way, this looks like it's x minus 1. But that's just an algebraic consequence of this particular matrix. Okay, and how about the eigenvalues? Well, spectrum of x is what? It's this lambda of f of lambda equals 0. And what is that? It's lambda 1, 2 are, so the trace of x, which is 1/2, and then, 1, and then over 2. And then plus minus, we have 1 plus, well, minus 4 times minus 1, right? over 2, which is 1 plus minus square root 5 over 2. And that's the golden ratio. So the spectrum is phi and phi bar, where we say that phi is 1 plus square root 5 over 2, and phi bar is 1 minus square root 5 over 2, and satisfies these, the Vieta formulae. So we'll have like phi bar equals minus 1, and phi plus phi bar equals 1. Okay, that's it. Short little snack for today. Hope you guys liked it, and see you in the next one.